So let's talk about ultrasonic interferometer. The ultrasonic interferometer is a simple device which is used to yield consistent data to determine velocity of the ultrasonic sound in a liquid medium. The ultrasound, which anyone knows, refers to the sound which refers to the waves with frequency which is above the audible range for humans, which is from 20 Hz to 20 kHz. So when an ultrasonic wave propagates through a medium, the molecules in that medium vibrate over very short distances, parallel to the longitudinal waves. We know that the sound waves are longitudinal waves, so the particles vibrate parallel to the direction of their motion. And during this vibration, the momentum is transferred among molecules, and this enables the sound or the wave to propagate through them. The ultrasonic sounds can be produced by different methods. There's commonly three methods. The first one is a mechanical method, which we use mechanical stuff or instruments to create this wave. And in this method, the ultrasonic frequencies range up to 100 kilohertz. But this technique is very rarely used due to its limited frequency range. So next is a piezoelectric generator, which is most commonly used method of creating an ultrasonic for this experimental situations. Here we know the principle of a piezoelectric crystal, which creates electric field, which creates oscillations when we apply electric field, and which generates an electric field when we apply pressure to it. So when a suitable electric field is applied to this crystal, it oscillates in such a way that it produces resonance when the frequency is matched, and this produces longitudinal waves or ultrasonic waves. And the next is called as the magnetostriction generator. The general principle involved in generating ultrasonic waves in this method, the magnetostriction method, is to cause some dense materials to vibrate very rapidly, and the vibrations produced by these materials cause the air surrounding the material to begin vibrating with the same frequency, and they spread out in the form of ultrasonic waves. So this is used to create ultrasonic waves in ferromagnetic rods like materials such as iron or nickel. And when the magnetic field is applied, small elongations or contractions occur in the length, and this is known as magnetostriction. And the change in length depends on the intensity of the applied magnetic field and the nature of the ferromagnetic material. So we have the velocity of a wave is related to its wavelength by this equation, where v is equal to lambda f, where f is the frequency of the wave, and lambda is the wavelength of the wave in the medium. If it is in the medium, the lambda is the wavelength of the wave in the air, and it depends on its medium. When it passes through a liquid, the wavelength changes. And the wave, when it is passing through a medium, the velocity of the wave is largely determined by the compressibility of the material of the medium. So it depends on this compressibility, the adiabatic compressibility of the fluid, and which is a measure of relative volume change of the fluid with response to a pressure change. So we have learned about adiabatic compressibility, which is the reciprocal of the bulk modulus, and the bulk modulus is defined as the ratio of the infinitesimal pressure increase to the resulting relative decrease of the volume. And this adiabatic compressibility of the material determines the velocity of the wave traveling in the medium. So the adiabatic compressibility can be calculated by using this equation, where the compressibility is denoted as beta, and beta is equal to 1 by rho v square, where rho is the density of the liquid and v is obviously the velocity of the wave passing through that medium. So now we are done with our equations and the theory of how the ultrasonic wave is produced and how to calculate the velocity in a given medium. So let us move to the procedure of this experiment. And in this experiment, we use the spectrometer. The standard interferometer uses a reflector and an experimental liquid which can be contained in the interferometer itself, and it is heated to a suitable temperature using a water bath. But here we are using a different approach. With we take the liquid in a rectangular dish, and we measure the values using a spectrometer. So let us see how we calculate or how we conduct this experiment using the spectrometer. So the preliminary adjustments of the spectrometer are made, which is to focus the telescope using a distant object method focus, and the collimator is placed to face the source, which is the sodium vapor light. So, and a rectangular glass dish is used, which contains a rectangular glass plate, and which is used as a container. And the dish is cleaned and dried up, and is filled with the suitable liquid for to observe the velocity of the ultrasonic wave. And here we use, for example, CCl4 solution. So the CCl4 solution is taken in a rectangular glass vessel. So, and the crystal oscillator, which is connected to an RF input, is placed inside this dish in the medium. So this crystal, this piezoelectric crystal, is placed inside this dish in such a way that it is parallel to the edges of the dish, and it is connected to a RF input which varies the frequency range. So after we place this crystal inside this dish, we vary the frequency of the oscillator. The frequency is varied in such a way that the crystal's natural frequency is matched with the frequency of the RF input. And when this happens, resonance happens. And the resonance happens, and the amplitude of the ultrasonic wave inside this medium is maximum, and acoustic resonance happens, and standing waves is produced inside this dish. The wave passes through the medium, and it is reflected back by the end of the rectangular dish, and inside a standing wave patterns is produced, and the amplitude is attained to a maximum when the resonance is obtained, when we change the frequency of the RF inputs in such a way that it matches the natural frequency of the crystal. And when this happens, acoustic resonance happens, and the spectral line which we obtain through the spectrometer, which we obtain through the spectrometer from the sodium vapor lamp, it is diffracted, and we see two spectral lines on either side. And the telescope is then made to coincide with the refracted lines which we see, and there may be more than two on either side, because there might be higher order spectral line diffractions, and the telescope is made to coincide with this spectral line on either side, and the result is noted. The vernier readings is noted for the vernier 1 and vernier 2. And the wavelength is calculated using this equation: lambda is equal to lambda dash sine theta, where lambda dash is the wavelength of the sodium vapor lamp, and the lambda is the change in the wavelength through the medium. Similarly, the wavelength is found for higher order values. So basically, what we do is we take the medium in a rectangular dish container, which is made up of glass, such that the waves can reflect inside, and then we place a piezoelectric crystal, which is connected to an RF input oscillator, and which is placed inside in such a way that the light from the source falls at a right angle on this liquid. And so the crystal oscillates, and waves and mechanical waves and ultrasonic waves is produced, which then passes through this medium, and which reflects back from the either sides of the rectangular dish, and an acoustic resonance is created inside this medium. And this acoustic resonance diffracts the spectral lines which is coming from the source, and we see diffracted spectral lines through this telescope on either side, and we calculate the readings. We note the readings on both of the vernier scales, and then we find the wavelength which is changed as it passes through this liquid. And so here we have the tabular column. So we can see that the number of tries, the number of verniers, vernier 1 and vernier 2, the left readings and the right readings, and the difference. The difference is calculated from either side, the left and right, for order 1 and order 2. And this difference is then, and the mean of this difference is taken. And then I've tried to mean 2 times. and then we find out the lambda dash. And using this lambda dash, we can find the velocity. The velocity here, v is equal to lambda f. We can substitute the lambda and the frequency is noted for which the resonance happens. So we can see the spectral lines diffracting, and this diffraction takes place only when the resonance condition is met, when the amplitude is has attained a maximum value. So we change the input of the frequency. We vary the frequency in the RF input such a way that this diffraction occurs. So when we see the value of the frequency in which we see the spectral lines with the frequency which we write down here, and the velocity is given by the lambda multiplied by the frequency. So using this velocity, we find out this compressibility, the adiabatic compressibility beta. We substitute V and rho. Rho is the density of the liquid. Density of the liquid which we have taken. For in this case, the density is 1594 kilogram per meter square. So that's all about this experiment. Thank you.